A giant walking, gesturing warrior robot is now on display in the port city of Yokohama, half an hour south of Tokyo.
A silent revolution is brewing in Japan's defense world. Towering machines with steel armor and powerful limbs are moving from the drawing board to dusty testing grounds. These giants promise to change the battlefield and push the limits of what robots can do. What drives a nation known for precision electronics to build towering combat machines? Today, we peel back the layers to see how these massive mechs came to life, what makes them tick, and where they could lead us next. But how did a fantasy rooted in anime and childhood dreams make the leap into real steel and circuitry? What moment sparked the rise of Japan's first true mech? Birth of Realworld mechs. Japan has long held a vision of massive robots walking on battlefields. For years, this idea lived only in cartoons and science fiction. People saw mechs in movies or comics and dreamed of piloting them. Early efforts focused on small models or machines that could not walk. At first, it seemed that building a true giant mech was far out of reach. Everything changed in 2012 when Suidobashi Heavy Industry in Tokyo revealed Kuratas. This giant machine stood around 4 meters tall and weighed over 4 tons. A single person could climb inside a small cockpit behind thick glass panels. Hands moved over simple controls to guide arms fitted with BB Gatling guns. This machine could roll at a slow walk on 4 wheels, hidden under heavy armor plates. Developers used parts from farm vehicles to power their hydraulics. Kuratas won attention worldwide through videos on the internet. Although it could not walk, this robot proved that engineers could build a large, piloted machine outside of fiction. Its design drew on Japanese anime heroes such as Votoms and Gundam, adding to its appeal among fans. In 2017, Hankook Mirai Technology introduced Method 2, a taller and more powerful machine. This robot reached about 5.5 meters in height. Engineers built a cockpit under a transparent dome where a pilot sits. Powerful hydraulic pistons moved its arms and legs with a force that could lift heavy weights. The body rested on 2 strong legs that looked like steel columns. Method 2 appeared to crouch and stand like a human. Developers attached sensors to measure balance and force. Heavy cables and support frames held it in place during trials. Tests captured data on joint limits and feedback responses from the pilot. This prototype showed that walking mechs might move from idea to reality, even if they needed more work. Researchers learned key lessons from both machines. Trials taught them how to balance weight, steer large arms, and keep movements smooth. They found that faster movements risked tipping over the machine. Safety systems, such as pressure relief valves and emergency shutdown switches, became essential. Small test rigs let engineers try new ideas before building full machines. They studied hydraulic fluid flow, valve response times, and sensor delays. Over time, these details improved. Engineers also worked on control consoles that felt natural to pilots. They tested joysticks, touchscreens, and even foot pedals. Each change brought the goal of a true walking robot closer. The gap between fiction and reality grew smaller. In labs across Japan, teams studied mechs day and night. As designs improved, Japan's defense agencies took notice. The Acquisition, Technology and Logistics Agency began funding research in 2020. Budgets shifted from concept art to practical tests. Engineers now aim to build mechs that can walk on uneven ground, cross rivers, and carry equipment. They plan to test in real fields, under trees, and over rocky soil. Work also explores adding cameras, thermal sensors, and light weapons. Researchers believe that a small squad of these giants could help soldiers with heavy lifting, scouting, or rescue. At this stage, mechs remain experimental projects. Soon, a world once limited to fiction may see these metal giants take their first real steps towards service. But what happens when artistic ambition collides with engineering precision? Could a statue built to honor fiction quietly become the prototype for war machines? From art piece to armed suit. Japan's love of large robots took a real turn in December 2020 when Bandai and partners unveiled the moving RX-78-2 Gundam at Yokohama. 18 meters tall and weighing 50 tons, it could move its head, raise its arm, and bend its knee with smooth grace. Hidden servo motors and custom gearboxes powered each motion. Hydraulic and electric actuators spanned its elbows and joints. Engineers placed dozens of sensors to track balance and load. The statue rode on a rail system that let it pivot and pose safely. Over 1 million visitors saw it in the first year. Tickets sold out within hours. This living statue showed that Japan could move massive parts with accurate control. The project cost roughly 6 billion yen, funded by private investors and government grants. Engineers partnered with local suppliers to create custom parts that could handle heavy loads. Behind the show lay key engineering breakthroughs. Custom software linked sensor data at each joint to a central controller. When the Gundam shifted weight, ankle pressure gauges and tilt sensors told the controller to adjust clamps and slow movements. Power cables and hydraulic lines ran up its legs to supply a smooth flow. Developers balanced speed and torque so that motions looked natural. They tested each sequence thousands of times on smaller rigs. Failed trials taught them where metal plates needed braces and how to cool motors under long demos. They also mapped energy use during each motion, noting peak draw during arm swings. This mapping helped size future power systems accurately. Lessons from these tests gave military teams a clear view of how to move heavy limbs under real conditions. At the same time, virtual reality training played a key role. Gundam Factory built VR simulators where pilots stepped into mock cockpits. These rigs used motion seats, wraparound screens, and haptic vests to mimic the feel of real weight. Pilots gripped joysticks to swing arms and pushed pedals to move legs. When a virtual limb hit an obstacle, the vest rumbled, and screens showed sparks. Each pilot spent hours learning timing, speed, and coordination. Data from these sessions recorded joystick patterns, error rates, and reaction times. Engineers used this data to refine control consoles on real mechs. Public Art in Yokohama also became a test lab for defense research. Ground Self-Defense Force observers watched each Gundam movement closely. They noted how software prevented overshoot when an arm reached its limit. Control programs automatically slowed motions near joint extremes. They saw how heat sinks and cooling fans kept motors safe after long runs. Bandai shared maintenance schedules and part lifespans. Service teams tracked wear on gears after each demo. Military officials realized that large mechs need regular inspections and modular parts that can be swapped quickly in the field. Next, engineers plan to turn these insights into armed suits. They aim to build a 5-meter-tall combat mech that can carry sensors, light weapons, and radios. Using proven servo control, balance systems, and training tools from the Gundam project, they hope test models will walk under their power by 2026. Public Art gave the blueprint. Now, Japan moves from showpiece to suit of armor, ready for the field. Under the hood, tech that powers giants. Moving a giant robot needs more than strong metal. It needs systems that work together smoothly. The main system is hydraulics. Engineers build hydraulic actuators that act like muscles. They use high-pressure oil to push pistons. Each joint has a cylinder, a pump, and a valve. When the pump sends oil into the cylinder, the piston moves. Valves control speed and force, so movements stay smooth. Oil lines run along the frame from tanks to joints. The tanks hold cooled, filtered fluid. Filters catch tiny debris so parts last longer. Engineers test each cylinder on rigs to find leaks or weak spots. They keep extra seals and hoses on hand so field crews can swap parts fast. Powering these hydraulics is a big challenge. Large robots need a lot of energy. Batteries alone become heavy and drain too fast. Teams combine a diesel engine with generators and battery packs. The diesel runs at a constant speed to drive a generator. The generator feeds electricity to pumps and charges batteries. During heavy moves, the robot draws on batteries. When it rests, the engine tops up the charge. This setup cuts noise and heat. In tests, a medium robot runs for 4 hours on one fuel tank and a full battery. Some groups test hydrogen fuel cells. They promise cleaner exhaust and less heat signature. However, they need special refuel stations and strict safety rules. For now, diesel hybrids offer the best mix of range and power. Sensors guide every step. Inertial measurement units track tilt and rotation. They sit near the robot's center and send data dozens of times each second. Laser scanners map obstacles ahead. Small radars spot moving objects. Force sensors in the feet measure how hard the ground pushes back. All these data streams into the control computer. The computer fuses inputs to build a real-time map of pose and surroundings. Simple rules tell the robot to slow a step if it senses too much tilt. It can shift weight to the other leg. Engineers program safe limits so the robot never leans past a set angle. Pilots control the giant with a human-machine interface. 2 joysticks move the arms and torso. Foot pedals shift the robot forward or backward. The touchscreen display system includes health, fuel level, and warnings. Audio alerts warn of overheating or low pressure. Some prototypes add vibration motors under the seat. If the robot strains, the seat shakes to give feedback. Training in simulators helps pilots learn how a giant robot moves. Virtual controls match the real console. This link between humans and machines remains key. Autopilot can help keep balance, but a trained pilot still guides the final moves. Steps on rough ground or sudden obstacles still need human judgment. Future updates may add a simple autopilot for flat ground. However, control still rests with the pilot. Research continues to improve each of these systems. While towering mechs grab headlines, could Japan's true robotic edge lie in something far more agile? Japan's modern robot army. In recent years, Japan's self-defense forces moved from single giant prototypes to whole fleets of smaller robots. After the Noto Peninsula earthquake in January 2024, the Ground Self-Defense Force deployed Ghost Robotics Vision 60 quadrupedal units. Each robot dog weighs about 30 kilograms, can carry 30 kilograms of sensors or supplies, and runs for 3 hours on a single battery charge. These machines navigate rubble and tight spaces that challenge humans and large vehicles. They stream live video back to operators, scan for signs of life with infrared cameras, and map damaged buildings using onboard LiDAR. Quiet and nimble, these dog-like robots proved valuable for search and rescue, showing how legged machines add a new layer to Japan's defense toolkit. Alongside legged robots, Japan ordered 3 Mission Master SP unmanned ground vehicles from Rheinmetall. These 8-wheeled UGVs will arrive with modular payload options. In cargo configuration, they carry up to 800 kilograms of supplies. Swap in a surveillance module, and they mount cameras, radars, and electronic sensors. Add a remote weapons station, and they deliver accurate fire support under operator control. Developed by Rheinmetall Canada and teamed with Japan's Marubeni Aerospace for local maintenance, Mission Master SPs can handle snow, mud, and steep slopes. Long-range batteries and hybrid drives let them work for 8 hours or more, making them ideal for logistics and perimeter security. In April 2024, Estonia's Milrem Robotics won a contract to supply the Japan Ground Self-Defense Force with 3 Themis-tracked UGVs. These low-slung robots travel on tank-like tracks, spreading weight evenly so they can cross soft ground and climb staircases. Each carries up to 200 kilograms. The modular design fits cargo pods, mortar systems, or sensor arrays. Operators guide Themis units from armored command vehicles or sheltered posts behind the front lines. In drills, they hauled ammunition, towed disabled vehicles, and cleared obstacles in simulated urban combat. Their quiet electric motors make them hard to detect, adding stealth to supply lines. Beyond ground vehicles, Japan tests bipedal carriers built by domestic teams. Backed by the Acquisition, Technology and Logistics Agency, prototypes about 3 meters tall can walk on 2 legs and carry 200 kilograms of gear. Trials at Camp Takeyama in Kochi Prefecture include slopes, wet grass, and gravel paths. Inertial sensors and foot pressure gauges keep the robot balanced. When a foot slips, the software shifts weight instantly to the other leg. Pilots inside a portable console guide each step with joysticks, while a heads-up display shows foot placement and system status. Though slower than wheels or tracks, bipedal carriers promise access to rough terrain that blocks other vehicles. Engineering units also join Japan's robot army. Mitsubishi Heavy Industries and other firms build remote-controlled tracked machines that dig trenches, lift debris, and tow heavy loads. One model uses an extendable arm to cut fallen trees or move concrete barriers. Operators control them from armored shelters far from danger. Chemical and radiation sensors added to these UGVs help scouts probe suspect areas before troops enter. Together with quadrupeds, wheeled UGVs, and biped carriers, Japan's robot fleet covers a wide range of missions: search and rescue, logistics, reconnaissance, and engineering support. As trials continue, these machines move in formation toward a future where humans and robots stand side by side in the field. Soldiers, plus machine, exoskeletons, and UGVs. Japan's interest in exoskeletons began with passive frames. In 2019, Panasonic showed its Power Loader suit. This frame wraps around a soldier's hips and thighs. Steel springs store energy when a soldier bends down. When the soldier stands, the springs release energy to help lift the weight. In tests, soldiers carrying 40 kilograms reported 30% less fatigue over 1 hour of walking. Maintenance is light because there are no motors or batteries. Soldiers only need to oil joints and check springs before each mission. Honda entered the field in 2021 with its walking assist prototype. Unlike passive frames, it uses small electric motors at the hips. Torque sensors detect when a soldier starts to lift a leg. The motors then add power to that movement. In trials at Tsuchiura Training Ground, soldiers carrying 50 kilograms could walk 20% faster on rough ground. The suit drew power from a backpack battery lasting 2 hours. Engineers focus now on making batteries lighter and extending runtime to 4 hours. Active exoskeletons from Japan's National Institute of Advanced Industrial Science and Technology add even more support. Their 2023 model, Suit W, uses motors at the knees and ankles. Each joint reads foot pressure and posture. When a soldier crouches or climbs, the suit boosts strength. In field drills in northern Hokkaido, soldiers climbed steep hills wearing full gear without extra rest breaks. Data showed joint load dropped by almost 50%. Researchers work on more compact battery packs and faster charge times to keep the suit ready in the field. Alongside human wearable suits, Japan deploys unmanned ground vehicles. Mitsubishi Heavy Industries built the multi-mission combat vehicle, unveiled in 2022. This tracked UGV weighs 10 tons and sports a 6-meter robotic arm. It can lift 500 kilograms of supplies or clear obstacles. Operators use augmented reality glasses to see the robot's view and control the arm with hand gestures. On a full tank and battery, it works for 8 hours. Kawasaki Heavy Industries developed the Kobelco KX, a compact CBRN detection UGV tested in 2023. It carries chemical and radiation sensors on a mast that retracts for transport. Operator stations at the camp relay data in real time. The robot crawls into suspect buildings, keeps troops back, and maps hazards. These systems work together in exercises at Camp Fuji. A squad sends out one exosuit soldier to lead and carry heavy gear. 2 robot dogs scout ahead. A tracked UGV follows with ammo and tools. If a path is blocked, the multi-mission arm clears debris. The CBRN UGV scans for gas or radiation. This mix of machines and humans cuts risk and speeds missions. As exoskeletons grow lighter and UGVs smarter, Japan moves closer to seamless teamwork between soldiers and machines. However, what's still locked behind classified doors? Are Japan's engineers quietly building something far more advanced than we've seen so far? Questions, rumors, and what could come next? Talks swirl about classified projects Japan keeps under tight security. Some reports say engineers test railguns mounted on robot arms. Railguns fire metal slugs at high speed with electric coils. Others claim labs try stealth coatings to cut infrared signatures and radar reflectivity. No official word confirms these. Insiders note that Japan's metal and electronics industry could support such work. Tests on rough terrain raise questions. Can a heavy mech walk over forest floors without tripping? Field trials show balance systems correct small shifts, but big impacts still topple prototypes. Engineers explore basic AI to plan stable footpaths. Real forests full of roots and rocks remain hard. Future models may use learning algorithms that adjust step patterns after each trial. Beyond prototypes, expect mid-size mechs about 3 meters tall. These could carry modular tools like anti-armor missile pods or CBRN detection gear. Designers plan quick change mounts, so a single machine adapts to many missions. Tests in urban and desert training areas may start next year. If successful, the production of small fleets might follow. Finally, Japan may join exercises with allied forces. Imagine squads led by exosuit soldiers, flanked by robot dogs scouting ahead, supported by mid-size mechs ready to lift gear. This mix of man and machine could change how troops move and fight. While full-size giants remain years away, Japan's careful steps bring this future closer with each test. Industry watchers ask if these machines will work outside Japan's tidy test ranges. Muddy fields, steep hills, and rainy weather could ground models. Future designs may add weatherproof seals, more robust sensors, and self-cleaning joints. Only real-world trials will prove if these giants can handle nature's tests. If Japan's giant machines keep evolving, we may see a new era of defense where humans and robots move side by side. What role would you want? Pilot, scout, or engineer? Let us know in the comments.